Right, okay, so I think I'm streaming now, and this is going to be something new. I'm going to read this, which is the guide to NumPy, and it was made by this guy, Travis E. Oliphant. It's written, well, it started, I think, in the late 90s, and then it became a product or something in 2006. I haven't read any of this, or I've read, actually, sorry, I've read the first kind of like 10 pages or something like that. Um, yeah, so we're just going to kind of like go through it. This was actually the creator, so sort of looked him up. Some other things. So yeah, other stuff there. What else did I have on that? I think that's kind of like it really. So maybe we'll just start going through the book. But I guess one of the pieces is yeah, NumPy is kind of like core to Python, and it's made it effectively what it is in terms of like one of the most powerful languages, not powerful, the most popular languages, I should say, around. And yeah, it's part of the data science piece as well, I guess. So yeah, data science is huge, and this guy kind of like it all started from Numeric Python. There's a great little there was a little video or something that I watched. I thought, you know, I'll go along and search for these documents, and this is the original NumPy document. I'm sure there's probably hundreds of the damn things. In fact, let me just Google it while I'm here. So we just go NumPy docs documentation. There we go. Um, so yeah, this is the I guess the latest, 25 version or something like that. Let's have a little look. NumPy documentation, tells you how to install it, all the rest of it, and so forth. But I guess I'm just going to focus on what's in the book, and we're going back. So we're going back like 20 years basically here in the book. So let's just have a little read through. By the way, let's just circle this piece here, 371 pages. So that's how long it's going to be, and that's what we're going to do is go through all of that. So, Guide to NumPy, this book is it's open source. I don't even know what this piece is, so let's have a little click on that as well. Whoops, let's go back. So that website doesn't exist, whatever that was. Let me just zoom in a little bit. Try that again. I'll try copy and paste. Copy, new tab, and paste. Let's have a look. No, there we go. That's how old it is. If you have multiple users at any institution, you should either share a single copy using one. Okay, fine, this is all a blurb. Like, some people will read it, some won't. It's been on the page long enough for you to read it, and you can pause and read it if you want. After October 31, this book may be freely copied. So there we go. It had an expiry date then in that case, 2006 to October 2021, 4 years life. Fine. You'll support temporary distribution. So NumPy from Python, the origins of NumPy. Basically, like I guess, like in a little video, he's a data scientist. This guy, really good guy by the looks of it. And he was just trying to solve some problems, and it was other people that built packages before, and he was trying to put the packages together. So that's kind of like the gist of it, really. So, I could sort of like browse through all of these bits, which I kind of like. You know what? That's nearly a video in itself, to be fair. Before we've even started on page 12, we've had all of these pieces. Let's have a little brief look. Object essentials. So he's talked about data types, basic indexing, which is slicing. So that's something that's very common in Python. Memory layout of the ND array. This is kind of like the most fundamental thing, I think. Again, I'm not sure that he was the creator of the ND array, but he certainly kind of like, he needed to use it, and I think pushed it into a way that was that made it much more functional for all other coders, basically. Universal functions for array, summary of new features, summary of differences with numeric. First step changes, second step changes, updating code that uses numeric, using alter underscore code n. I don't even know what that is. Let's have a little brief look at that if I can. I can't copy the actual thing because my mouse turns into a thing. Alter underscore code n. I wonder, there we go, how to update data type after K. I wonder if that's got anything to do with it. Not sure. Oh, look, somebody's messaged on my typing this morning, Python versus VS Code. Ah, yeah. People seem to like this one. Getting sidetracked a tiny bit, but since it's an open video anyway, I'm allowing myself to be sidetracked. Yeah, we'll go back to that anyway. I think that was long fixed, by the way. It's got 16 votes. Very nice. Ah, I should actually mention the book. This is the book on Python somewhere. There we go. So, Python programming, top of the stack, and that's basically how to get. There was a little book on how to get your rating up on Stack Overflow when it existed before large language models existed. Everyone was using that website that I was just on, so that's kind of like a good reminder. Yeah, go buy the book. That'd be quite nice, and put your comments on. I wonder if anyone's got any good comments on this book. So we'll see. Anyway, outside of that, summary of differences with NumArray. So I think this was the original package that was used, which was Numeric, or at least it was two like competing packages. One was called Numeric. So this one over here, and the other one was called NumArray, and they kind of like joined up, I guess, in some way to become NumPy basically for Python. And yeah, it's like a core thing. In fact, it's not a built-in library. You have to pip install it, but it's kind of like used basically everywhere, pretty much. I wonder actually but I mean for sure it will be here because I must have pip installed it. Let's just do maybe I'll even make a little folder. Well, I've got a test folder here. Test pandas, but no test NumPy. If I've got pandas, then I'll have NumPy. So I guess it's test underscore NumPy.py return. And I wonder what the AI does from there. If name equals, I'll just do that just for the start of it, and then I'll do define a main. Oh, actually I got the main template. There we go. Always do that. Right, so that's my setup. Plus. Maybe I'll get rid of this piece over here on the side. Go down there a bit. So that's the code, and then all my imports go here. So import NumPy as MP. Great, we love the AI coming in. And actually, I'm quite happy that this happened in a way because NumPy could not be resolved Pylance, and I've got to have to do a pip install NumPy, which the AI will tell me that. So, for example, if I go there and go onto Bard and start a new chat, and in the new chat paste that in there. There we go. It's going to recognize what I'm asking as a question. I might actually just make this bigger just for the sake of it, so that I can zoom in a little bit, get rid of this bar on the side. And it says pip install NumPy. It always gives you the bash. I hate the fact that it gives you the bash because I use Windows all the time, but since pip install NumPy is the same, that's cool. So, and we can see here I'm in a virtual environment. VS Code now makes you virtual environments quite nicely. It was only about a year or two ago. It was really ugly virtual environments, but now it's quite helpful. A virtual environment is like a self-contained environment, so if you pip install something. So I only just made this virtual environment. So if you pip install something, it's contained within the environment, so it doesn't pollute elsewhere, and it's for version control basically. So because I just made this new virtual environment, it's not going to recognize any packages, so it didn't recognize NumPy in the linter, could not be resolved, so I'm going to do that, which is pip install NumPy. So you actually get the full thing. like the version, whatever it's called, pip installing it, collecting my packages, and where do these things go? Somewhere in, I guess it's in the virtual environment. Is it library and scripts basically? Yep, NumPy is making its way in there. So the pandas thing that I had, pandas lives on top of NumPy, that'll be in there too. So we've got all of that pip installed while I was talking, and new release available. Okay, let's just upgrade pip as well. I don't even know why I'm doing this, but I will for the sake of it. I always like everything to be current. Just annoys me that they're not. This will run in the background anyway, so let's just jump back to the book. So you got this array object. This is kind of like the core of everything, I think, which is the ND array. So in fact, when it does work, other attributes. Okay, ND array methods. So you've got this ND array. You've got this kind of like object, which is an array, and we'll kind of like. I wonder if you know what I'll do. I'll do a duplicate, and the reason why I'll do a duplicate is plus plus. Is if I want to jump around somewhere, maybe so ND array. We are going to get to this piece anyway. It doesn't have that piece, doesn't have that piece. So this is all I wanted to show what an array was. Is this piece here over there? But basically, for intents and purposes, we can think of an array as like this block of memory that's got rows and columns. So that's effectively what an array is. And you have to index the array. So these are the i's and these are the j's. So for example, this is an array in computing start from 0, 0. We'll go through all of that piece, and it gets all the way up to n and m, for example, like the largest numbers. And you have to have a method of counting. So this is like row 0, this is row number 1, this is row number 2, and so forth. So this cell here is 0, 1, 2. So this is 0, 2 in terms of positioning for the index, and this is 1, 2, and this here is 2, 2, 2, 2. If my numbers were written nicely, we'd see that a little bit better. So clear that, and let's continue. So yeah, you've got this array, but the nice part about it is you get all of these methods that go on the arrays, I guess. So you get the array methods, that's page 54. You get the special methods. I don't even know what it's classified as a special method, but we'll find out. Array indexing, so basic slicing, basic routines, creating arrays. So I'm just going to jump back, and this for sure will be okay. All the pip, it's all done. And from the main I'll call other functions, but basically even before that, actually before we do our like modular programming, well actually I will, maybe I'll keep it in here. Def something like make array, right? Function to make a NumPy array, and oops, there we go. I like to have that. A is a NumPy array, and then return a, or actually let's just do print a. There we go, and that's it. We're going to call this function from our main function. So make array. There we go, and we can just run our code. So, I mean, this is basically Python. Like what Python does is it starts from the if. You don't have to write code like this. You can write it as a script, but I like to run all my code as like functional code, should I say. I don't know if anyone can see the mini map up the top corner there. Like right there, there's a little mini map. It'll get bigger and bigger as we code. If we code, I don't know if we're going to code. But we're just going to do make array, which is going to, so the main function is defined here. Another function is defined here. Python runs its code sequentially, and then it gets to the if name equals main, and then it sees if name equals main. It goes and runs this piece of code, the main function, so it goes right back to the top, and it calls make array. So a nice little convoluted loop to start with, but it's kind of like the pattern that's always there. So Python reads its code sequentially, It's read the fact that there's a main function here. It's read the fact that there's a function here. And then this is the first actual piece of code. Now, this piece just checks if this is the main file, and it's more for projects than anything else. So that's a bit there. But here's the first line of code, really, which is on line 27 at the moment, which says run main. And what it does is it goes and runs main, which is in memory. And inside main is only one piece of code, which is make array. So make array goes and runs make array, and make array then instantiates a NumPy array, an np.array, and finally we're going to print the array, and hopefully, if that all works, the result will get printed over here. So that's basically it. How many steps did we have in this code? One for traversing down, I guess. The fact that I have to understand. We'll call this step 2, which is basically reading of the main. This is step 3 here, which is reading the main. This is step 4, and I guess we could call this sort of like step 5 over there. And our observation, I guess, is down here, which is step 6. That's the result. So little tick if it works. So just let me hit the run button, F5, to see. I've got to launch a debugger because it's the first time I've done this. And we can see it's running down the bottom. And there we go. We get our little array down the bottom there. So that's pretty much it. The only piece was my arrow wasn't quite in the right place. I'd have to put the arrow here because it makes a new line. There we go. Point the arrow right there. So that's basically it. So we've created a NumPy array. And let's go back. Right, basic routines, additional convenience routines. Bear in mind that this is 20 years old, so NumPy is way better and probably way more different. And maybe a lot of these things are legacy. Although, for example, dtype, the data dtype objects, they're not legacy. So again, if I go to, I wonder if I can go to dtype and see what, yeah, there we go, ping data dtype object. So I guess we'll read a little bit about it, but the dtype is it's NumPy uses C++, kind of like in some way uses a C++ types and like an int and a an interval, a string, and so forth, and they're all of different lengths, and that's the key piece about numeric Python or NumPy, which is this contiguous block of memory that it will talk about. And in order for the memory to be a contiguous block, you have to know the size of the elements. So you kind of have to fill it up with either integers, in which case an integer is like 8 bits. So each each unit is 8 bits. So that's how you kind of like define and know your space. If you had strings or something, it'd be longer, and so forth. But yeah, I guess we'll get into that. Scalar objects. So we did detail by standard classes, universal functions. Okay, broadcasting output type. I don't even know necessarily what it means when it says universal functions per se, but I've kind of got an idea maybe. Basic modules, so linear algebra. Okay, again, discrete Fourier transform. Okay. Fourier. Ooh, missed. Control F. Nope, got too long. There we go. Discrete Fourier transforms. I should have typed in FFT, the fast Fourier transform. Ping. Discrete Fourier transforms. All the algorithms here are most efficient if the length of the data is a power of 2. Okay, I've got to remember all of this stuff back from my physics day, also about 25 years ago, funnily enough. So I was actually, the funny piece is I was a graduate when all of this was being made and built and so forth. So in 98, I didn't even know of the existence of Python, probably until about 2016, I reckon, when I left Commerzbank and decided to look into new languages and like retool up and see what was out there. And somebody said, well, why don't you use Python? I kind of like ignored it for the first 10 times because JavaScript, in a way, Node.js almost was like felt like the most complete language that I've ever used, to be fair. Even though I know that like C++ is kind of like, you know, the thing, you know, and Java's out there and so forth. But yeah, Node.js was just basically better. But anyway, all the data science use Python, and quite a few, well, one or two people who I was always collaborating with, like, why don't you use NumPy? Why don't you use Python? Why don't you use Python? Python will do it. Python will do it. Python's like built for that. And I was like, okay, fine. I didn't like the white spaces in Python and the non-curly braces. It's something that you need to get used to. Still not a billion percent, but I guess, and it forces you to position your code in a very regimented way, for an interpreted and like loosely typed language is the opposite of what you think. But when you get used to it, it's clean. Anyway, let's get on. Basic modules. So linear algebra, discrete Fourier transforms, random numbers. Okay, testing and packaging. I've got a testing thing, and actually, funnily enough, you know, like when I say I don't do any testing, there's all of these test things, but I've never used the testing in the same way. But by the way, this testing is probably not going to be anywhere close to what modern testing is. But it'd be interesting maybe to see what that is. C API, new Python types and C structures. So, you know, Python's going to talk about C. You'll never get away from like a deep Python without knowing what C is. And I mean, I guess a C structure is a bit like a Python class in a way. It's a struct in C and a class in Python, as in it's literal. But you know, we'll go through that. So new Python types defined. So I think this is maybe where it moves a little bit away and becomes Python as opposed to like just C. C structures. Then there is the complete API, so I wonder what that is. Configuration details guaranteed to be defined. That's an interesting one because yeah, that's an interesting one because I always have issues with this in Python, at least compared to other languages, in the sense that you can have any types, for example. So I wonder if that's what it refers to. Max min values for integers, okay, C types, boolean, signed, unsigned. So we'll go through some of that. Creating arrays, dealing with types, array flags, array methods. So you can see everything here is about arrays basically. But arrays are going to be essential. This is why Python has become so important as a language in data science and machine learning, because we're literally living in a world of arrays, you know, things like TensorFlow and so forth. But all of the AI and machine learning and so forth, there's huge amounts of array matrix manipulation and so forth. How to extend with NumPy, writing an extension module. Okay. Functions without keyword arguments, functions with keyword arguments. It's going to be interesting to see what this kind of stuff looks like. So I'm just going to type in here Control F, keyword arguments. There we go. And go to functions without keyword arguments. So functions that don't accept keyword arguments. Static pi object. Well, I don't think static. I wonder what. Let me just stick this in here. Oh no. Okay. This is some C code. So that's what C code looks like. Functions that don't accept keyword arguments. So keyword argument is like an argument. That is the, well, maybe we'll get around to it, but it's an argument that comes after non-keyword arguments. Basically, you don't specify what it is. So, for example, here at the moment, I've got this function make array. It's got no arguments, but maybe I wanted to have an argument like the size. So, length of array, len array. Len of array equals 5. Now that's a keyword argument because it's put equals 5. It's almost like, I think it's almost like defined the size of the array for the user. So if I call this function here now, well, we can see in the type hint, it's an integer that it takes in an integer of size 5 basically, an integer 5, and that's because it knows that there's 5 elements in this array, so the AI has done it. But if I said 6, then it would be 6. Now here, then I'd need to write my code in a different way. So a equals, there we go. So and this is, by the way, so this is one of the functions that probably will come about, but I've now defined an array of zeros. So where we see, I'll just comment this out actually rather than deleting it, where we see this array down here at the bottom, so this piece over here, we've got 1, 2, 3, 4, 5. This pretty little function here just makes an array of zeros, but it's actually going to make 6 of them now because the length of the array is defined here. So it's like np zeros of value 6. So when we run the code, if we look down the bottom of the code, so if we look down over here, we're going to get some extra pieces, and I'm just going to modify it a little bit, which is I'm actually going to keep the array of zeros there. In fact, I'm going to turn it to a B, and escape, I'll just move it down one line there, because we want to then print it straight underneath. Oops. B. Tab. There we go. I have to tab to finish the autocomplete. I really like the what do we call this little thing here? Our little chat. The IntelliSense that goes on. So, what is that extension called? Scroll down, scroll down, scroll down. I'll find it. I promise. Oh. No, it's not in there. I thought that extension, well, maybe it's just built-in extension straight away. Let's get rid of that anyway, because we don't need it on the side. But it's the VS Code AI. What is the VS Code AI called? Question mark. It's going to give me a full thing. Yeah, Copilot, that's what I was looking for, GitHub's Copilot. Anyway, let's just run this. So F5 to run it. And we see an array of 1, 2, in fact I'll circle those little pieces. 1, 2, 3, 4, 5, 6. 6 elements. I wonder if in this array, and we can already see sort of like the D types, in this array, if I can, you see these dots after them, that means that it's a bunch of floating point numbers. I wonder if I can set the D type equal int32, there we go, and just run that again, F5. Oh, it's still got the dots afterwards, because I thought it was an integer, so I wonder if I make that int8, if that's any different. Oh, whoops, take that back. I needed to put the D type X over here if it allows for a D type. I think it does. F5. We're going to see all the little dots disappear, hopefully. There we go. Now they're integers. So the dot means floating point number. That's little hints. There we go. And there's 6 of them compared to 5 there. And the reason it's 6 is because of this keyword argument. So let's jump back to the docs. Over there and over there. What else is there? Using Python as glue. This is kind of like, there was another book written, I think Python automate the boring stuff or something like that. It's quite an interesting, the title of the book's quite interesting. The contents weren't as great, but like basically Python's an amazing glue language. It sort of like sticks all other codes kind of like together and so forth. So yeah, having a shared library, additional tools, what you may find. Okay, what's swig? Additional to. I wonder if I can open a new. Okay, fine. Codex explanations. Okay, memory model, data type encapsulation, and the iterators. Yeah. So this is how it was all done 20 years ago, right? List of tables, built-in array scalar table corresponding to. Right, so let me just take this, copy that, and then go Control F3, list of tables, and click on that. Yeah, so this is all the different types that are available. So list of tables, attributes of the ND array. So yeah, different things, different attributes, methods, and attributes that you can have. So again, I'll go back. Array conversion methods as types. So this is typecasting to other types. You can copy an array. Okay, dump. Okay, this is all really crude, by the way. Like, so, you know, the NumPy docs here, or even if I want to do copy NumPy array, you know, it's going to take me to a few different places. You know, in the docs, W3 schools, and our favourite deep copy of an NumPy array in Python. A whole big discussion on Stack Overflow will no doubt assume I have a NumPy array of different I have an array of different arrays. Great question. I have an array of arrays, and I want to make a deep copy of the arrays. I found the following. So, anyway, is D the best way to do this? Is there a deep copy function I missed? Right. Interesting. A deep copy is different from a copy because when you copy an array, you copy the. So imagine the array is just sort of like some sort of listing here, and these are all the elements of the array. So this is just a one-dimensional array. These things are now pointing to other arrays. So more arrays over there. That one's pointing to this one. Now, if you change this value, I think, if you change a value in one of these, in one of the sub arrays, will it be copied across or not copied across, basically? So, so if you change one of these values inside, this piece still points to this, but it might not point to that because of the immutability of arrays. That's kind of, so therefore one might need a deep copy, or at least if this points to another array, I think, yeah, at some point you need to be doing a deep copy. So that's kind of like what it's about. Oops, part of my drawing is actually not on the thing, so let me just, if I can, move it. There we go. So like arrays pointing to other arrays. Anyway, off with that. Let's go back, see what else is in this book. So that's the end from part 1, NumPy from Python. So NumPy was from Numerics, and it's the Python version of Numerics origins. NumPy build-ons, and there's NumPy builds on, and is a successor to the successful numeric array object. Its goal is to create a cornerstone for useful environment for a useful environment for scientific computing. In order to better understand the people surrounding NumPy, its library, I will explain a little bit about how SciPy and current NumPy originated in 1988. Studying my biomedical. I came across Python and its numeric extensions, and its numerical extensions called Numeric, while I was looking for ways to analyze large data sets for a magnetic resonance imaging and ultrasound using high-level language. I quickly fell in love with Python programming, which was a remarkable statement to make about a programming language. If I had not seen others with the same view, I might have seriously doubted my sanity. I became rather involved, blah blah. In Numeric Python, the community, adding the C API chapter to, okay. So a lot of credits to a lot of other people, and and things were built before, things were built after. This is kind of like one little chapter in the history of one of the best modules, I guess, most prominent modules of coding in the, I guess, in the earliest 20th century, that's for sure. And it was just fashioned out of a need, basically, by operating this in this immediate make it fashion. I ended up with a substantial library of extension modules that help Python and Numeric become easier in a scientific setting. These earlier modules included for output functions and so forth. Okay, here's a little interesting bit. While I was doing the laborious work, some other guy noticed that a lot of the routines I was wrapping were written in Fortran, another language, an old language, and it was no simplified wrapping mechanism for Fortran routines like Swig for C. So there we go, then we now all know what Swig is. It's a wrapping mechanism for C. He began the task of writing FTPy, which probably stands for Fortran to Python, which made it possible to easily wrap Fortran programs into Python. I helped him with a little bit, mostly with the testing and contributing. I know, but okay, so a lot of this was someone else's work. So what you have is something like you've got Fortran over there, and it's got lots of functions and things that can be used, and you've got Python over here, and somebody had to build a translator, and that would have been key, so that you could basically use this the extensive work and library, the extensive works of everyone that contributed, I guess, to the Fortran library, and bring it over to this. I will call it a newer language. It's newer language, Python. So one language is sort of like using the other, and Python uses a lot of other languages. So it's one of its. I'm going to say it's one of its advantages. When I finished my PhD, Eric Jones, who came to me, had a collection of Python. So someone had a collection of Python modules had developed, and he wanted to combine these modules all into one super large package, and that's kind of like what these guys set about doing. At the start of 2000, SciPy was released, so 2005, giving us context in terms of dates and times, was released and stable for early November. Part of the reason it was difficult to stabilize SciPy was that the array object upon which SciPy builds was undergoing a bit of an upheaval. At about the same time as SciPy was being built, some numeric users were hitting up against the limit capabilities of numeric, in particular the ability to deal with the memory mapped files and associated alignment and swapping issues. So memory map files, record arrays, altered error checking modes were important but limited and non-existent in numeric. As a result, Numeric was created. So another set of people by these guys here, by Perry Greenfield, Tom Miller and Rick White at the Space Science Telescope Institute as a replacement for Numeric. So you've got these two things, you've got Numeric and you've got Numeric. So these two things over there. Numeric uses a very different implementation scheme as a mix of Python classes and C code, which led to slowdowns in certain common uses, while improving some capabilities. It was also slow to pick up on the more advanced features of Numeric's universal functions, ufuncs, never recreating the C API that SciPy depended on. That made it difficult for SciPy to convert to Numeric. Okay, so you just got these two things. You've got Numeric, Anyway, many newcomers to the scientific computing with Python were told that Numeric was the future and started developing for it. Very useful tools were developed that could not be used with Numeric. Right, so you had Numeric and you had Numeric, but you couldn't use them together. This state of affair was very discouraging for me personally, as it left the community fragmented. Some developed for Numeric, others developed as part of SciPy. So, and this happens a lot, by the way, in all, like, it's not just coding, it's everywhere. A few people even rejected adopting Python for scientific computing entirely because of the split, and that splits will do damages. It's almost like you're bifurcated. Splits of hurt. For example, Windows dominates, and then you've got Mac. That kind of like it's got its own community, and then you've got Linux. And Linux is open source and free, but Linux bifurcates into or because it's open source and free, it's like everywhere. So like it's fragmented, and everyone's got their own opinion and version of what's the best in this version and so forth. Whereas when you've got like Windows here, so that's like Windows for example, or you've got Mac here. I don't use Mac, but there's one version, and the entire community is sort of like building for that one version. So even though you can't like delve away from it, and these things are called forks, you still like can't fork out. It gives you like a split. Everyone's building towards a common cause, whereas sometimes the decentralized things have that weakness, should we say? And it could have happened to Python, could have happened to NumPy. It didn't. That combination of joining Numeric to Numeric, I guess, so they made NumPy what it is. So it should be recognised that split was not intentional, but simply out of growth of the different and exacting demands on the side. Yeah, exactly. That's pretty much it. Yeah, he's not assigning blame to anyone. It's just the way that these things are. So anyway, using a strict biology, it is only through the process of dividing numbers. I think this concept applies to NumPy. Yeah, it's only through the process of dividing and merging that better results are born. Yeah, that's pretty much long and short of it. In early 2005, I decided to begin an effort to bring the divergent community together under a common framework where possible, to make SciPy work with, as a core. After a couple of days of studying Numeric, I was not enthusiastic about its approach. My familiarity with numeric code was no doubt biased my opinion, but it seemed to me that the features of Numeric could be added back to Numeric with a few fundamental changes to the core object. This would make the transition to SciPy more enhanced array object much easier. Therefore, I've begun the construct of this hybrid object. Okay, fine. Note, I'm jumping forward a little bit. Oh, actually, let's have a look here. This book is only briefly outlined some of the infrastructure that surrounds the basic objects of NumPy to provide additional functionality contained in the older numeric packages: linear algebra, random array, fast Fourier transform, FFT, fast Fourier transform. This infrastructure in NumPy includes basic linear algebra routines, Fourier transform capabilities, and random number generators. Funnily enough, when I was coding and doing all of this stuff, I was doing a lot of it in C++ actually. So I don't even know if it was C++, it might be in C. In fact, I think it was C because I was using malloc and calloc. No, I think they're part of C++ too, so I still don't know. 25 years ago. In addition, the Fortran to Python module, F2Py, the FTPy module, is described in its own documentation. So it's only briefly mentioned in the second part of this book. There are also extensions to the standard Python utils. Okay, anyway, let's jump on. Note, the NumPy namespace. The word namespace is interesting. It's used in C++. Again, like all of the themes in one language, or many of the themes in one language, are adopted from other languages. So the namespace is one of them. NumPy namespace includes all names. Bless me, I had to sneeze. And it includes all names under the numpy.core and the numpy.lib namespaces as well. Thus, import NumPy will also import the names from numpy.core and numpy.lib. So yeah, I guess you've got NumPy over here, and you've got NumPy.core here, and you've got NumPy.lib here. Oops, NumPy.lib over here. So they're like subdirectories, but everything is sort of like exposed here in NumPy. So when you do your import of NumPy, finally, when you do import it, you get everything. Like that's how it's built. So very nice. Python allows for that quite nicely. So yeah. Right, subpackage, core, lib, linen, linalg, linear algebra, linalg, FFT, discrete Fourier transform, the old. Okay, so it's kind of like saying what things are, I guess. Basic objects, all names exported to NumPy, so that's the core. Lib, additional utility, so obviously extra pieces were made. All names exported to NumPy. So everything there is exported. Basic linear algebra, old linear algebra. So this is stuff taken from Numeric, a package or something that I've never seen exactly. What I'm going to do actually is do in here, I'm just going to do it just to see what comes out. Example code from Numeric. And I'll put something like short answer. Because I don't want to see the whole. Right, there we go. Let's see what comes out. You asked for example code from a library named Numeric. However, the most widely used and most numerical computing library in Python is NumPy, which is short for numerical Python. The original numeric library is outdated and has been replaced by NumPy, so it doesn't even give it to me. Here is the shortcode using NumPy. Show code specifically from Numeric. Boom. Right. Import Numeric. There we go. So beautiful. Look at this. You've got a numeric array, which is the same as the ND dot array or the NumPy array. Over here, np dot array. So you've got the numeric, and then you've got your array, and you've got something here declaring the type that's in there. And here we are going to guess that they're integers because it's a numeric dot int. So create a numeric array. The type code parameter was used to specify the data type, but now we use, doesn't show it in here, but it did show it in the code that I wrote, the data type, dtype. So it's funny that, like, you know, I wonder if it'd actually have been nicer or better to call it data type or something. Like, it's got type code here, we've got dtype, why not just call it data type? But anyway, Celebi, that's what all of that is. So let's just go back. Random number generators. Yep, okay. The old random array from Numeric. Let's just bang that in. Boom, old random array from Numeric. There you go, random array. So, like, this stuff manifests. We can see where it's actually lifted. It's interesting to me because I've not actually done this before. So, def make a underscore random array of length thick. Okay. And rand int. So a similar type of thing in a way. Array random of length 10. Let's have a look. I'm just getting some messages down the side. Alright, report spam and leave. Yeah, so you've got the rand int there, and what do we have here? We've got a random. Okay, funnily enough, import numeric dot random array is random array. Okay, fine. So No, this code is for historical context and will not run it in a modern Python environment. We've moved on. So some code lives on, others doesn't. There are other ways of creating random numbers in Python. Make a list of random numbers. But I don't want to make an array of random numbers, so make a list of random numbers. Not using NumPy. Right, it's still promoting this, right? Control Z, didn't want that. Right, so where is my little piece of my little snippet of code? Sorry, I did Alt tab there. Let's get it back. Just do a list of random numbers, not using NumPy, so using for loop. Yeah, that's it. You just use a random module here, so let me just copy that. So go back up to the top and import random. Oops, didn't want all of that. Control Z. So import random, and then over here, where is it? It's a bunch of random, so I'll just do random, not random, basically. But we can see the similarity. We're going to use NumPy, but you could do num random number equals random dot random without the, I think that should be, and then like here we do print random number, and we'd have to call this, we're actually like, the IntelliSense has put in 6, I'm going to make it 10, there we go, since it's already there. Oops, 10. So an array of random numbers from 0 to 100, there we go, and also we're going to get that. So we're going to get 2 extra bits down the bottom when we run this code, assuming that of course we call it here, so we shall do. The thing about the keyword arguments is you don't have to use them, so I'm not going to use 10, I'm going to use 8. There we go. And run our code. Boom. We get a list of 8 random numbers between 0 and 100, I guess. Between 0 and 99, I think it will be, because it can't do 100. Yeah, 1, 2, 3, 4, 5, 6, 7, 8 of these, and then we also get a random.random. This time it's a float, not an integer. Here, I guess it tells you that it returns, therefore random returns a float. So it's quite nice. A lot of, if you type hint and if things are type hinted well and if modules are written well, things weren't written as well as they could have been, but that's because type hinting never existed. The modern editors give you all of the like clues and hints and so forth about how a function actually works. So like if I hovered over this function that I built myself, it kind of like, it's called the function signature. It gives me the arguments that go in. Here it's telling me that it's a keyword argument because it's predefined as int equals 10. Now I could leave it as that, or I could have something else. And it also tells me it doesn't return anything back. So I could have actually returned the random number back, for example, random number, and then straight away it should realize, yeah, look, it's returning me back a float. I could actually have declared that this is, I think we do the declaration like this, float. Yeah, there we go. So I could actually specify that. I wonder if I put in what it would tell me it's giving back. It does, it supersedes it. It says an int, but actually I'm giving back a float. Naughty me, Python allows it. Python's not going to throw you an error. Another language like C++ certainly would throw you an error. Python's not going to throw you the error. So, yeah. Let's just continue then, shall we? on to we'll go back then. So that was on my little delve into random. Disutils enhance build and distribution, improve builds on standard distribution utilities. Basically, this is for distribution. I've never really done much distribution. Also, unit testing. I've never really done much unit testing either, although it's a key part of coding. So, utility functions used for testing. F2Py, automatic wrapping or Fortran code, a useful utility needed for SciPy. So, anyway, chapter 2, Object Essentials. There's a little tip here. I'm always inclined to read the tip first because it's in bold and blue and in the box. All arrays in NumPy are indexed starting at 0 and ending in m minus 1, m being the length, I guess. Yeah, I would always say n minus 1, but it's m minus 1. NumPy provides two fundamental objects, an n-dimensional array object called the ND array, and a universal function object, ufunc. I don't even know what that is yet. In addition, there are other objects that build on top of these, which you will find useful in your work. The current chapter will provide background information on just the ND array and ufunc. That will be later, important later. So the ND array is an n-dimensional array, and it's a homogeneous collection of items indexed using n integers. Right, that's interesting, but I guess that's where like a lot of this other stuff comes in, because it doesn't have to be integers, but it has to be homogeneous. That's the key word, which means all of the same type. So nice long word, an array with elements that are all of the same type. There are two essential pieces of information that define an n-dimensional array. One is the shape of the array, and two, the kind of item it is composed of. So the indexing is just integers. That's cool. Okay, fine, yeah. So we've got this shape, and we've got what's contained in it. So the shape of the array is a tuple of n integers, one for each dimension. That provides information for how far the index can vary along the dimensions. The other important information describing the ND array is the kind of item that the array is composed of, because every ND array is homogeneous collection of exactly the same data type. Every item takes up the same size block of memory, and each block of memory in the ND array is interpreted exactly in the same way. Now that's, this gives the speed. You get this contiguous block of memory. We know exactly, it's well defined. We know exactly how big it is. I guess it's going to go here anyway, but we've got, for example, consider the following piece of code. A is an array. So you've got this array. This has got two dimensions. This is the first array, and this is the second. So it's like a list. It's 1, 2, 3 on the top row, and 4, 5, 6 on the next row. And funnily enough, I think this will just work in the code. So that's why I've got this thing up actually. So I'm going to do def the book. There we go. Colon, and then do that little piece of code here, and then return a. And we notice straight away that we've got this squiggly thing because array doesn't exist. Array is not defined. My rough editor says, but mp.array is allowed, and that's because it's coming from NumPy. So not bad, this old piece of code. Yeah. And we can do a.shape. So here, we're not even going to return it actually. We're going to do the print a.shape, and we're going to print, in fact, a.number dimensions. I guess is the ending. Oh, well, actually, it's the a.dtype with the bit. There we go. it's guessed it. You can see all of the pieces, by the way. So in Python, you don't have to finish your functions with a return. This just means it will return nothing, returning none. So it's just going to run a little block of code. So this is about the book. So tab here, the book, and we're just going to run that, and we're going to get the shape of this array, which will be a 2 by 3, because it's 2 rows. These 2 blue things, 1 row, 2 rows, and each row has 3 elements in it. So when I hit F5, and then we'll get the number of dimensions, which is, I guess it's going to be 2 here, and then the D type, which is int. So let's just run that, and we get the 2 by 3. It's got 2 dimensions. I guess that's because this is 2 here, so that's a 2 dimension array, and they're of type int 64. Now again, like we could have put in here D type and then int 16, because we didn't need to use 64 bits of memory. So and that's the thing about this array, right? This one where it didn't specify the D type before. So imagine that wasn't there. It's going to allocate, basically, so like 60 these blocks here, right? That's the first 3 elements, and that's the next 3 here. That's my really bad drawing, right? But if it's D type 16, basically my block's a little bit smaller, so I'm a little bit more efficient with memory. So it's kind of like that. The first one, this one here, is the type 64, whereas this one here is of type, the D type is 16, so 16-bit integers. That's basically it. So yeah, we got that. We see here the default is in 32. Well, I'm using computer 25 years on, so there we go. For all code in this book, it is assumed that you have first entered import from NumPy import star. Now this is really, this is deemed to be really bad practice, but this is what existed 25 years ago. It means import all of the methods. This is called the wildcard import all of the methods and modules, but that would pollute the namespace. So that's what's referred to up at the top here. Import NumPy as NP. Then we can expose things carefully, rather than if I did it from NumPy. I wonder if that's the same thing actually. Yeah, it is. From NumPy import star, that's going to import everything. Now let's have a look at the squiggle. From NumPy import star used, unable to detect unidentified names. It's basically like the modern documentation will give a squiggle. Documentation is available in 2 forms: docstrings provided with the code and loose standing reference guide from the NumPy homepage. I wonder if that points to the correct NumPy home. There we go. Let's see what. Yeah, it does. Is that different to this? No, I think it's pretty much the same if I put them side by side. Yeah, they're the same thing. It's just a different page on the page. But anyway, we recommend exploring document using IPython and using advanced Python shell, tab completion, and so forth. The docstring example assumes that NumPy has been imported as NP. Right, there we go. Use the built-in help function. It just helps identify where things are from, because then if I do put something like array, right, equals this, it's kind of like allowed, right? So before, the rough editor and linters and all of that, this was like deemed to be bad practice. It is bad practice. I just never do it. Whereas if you do np dot, the linter understands, it exposes all of the methods and attributes of this object, whereas here everything's automatically exposed. So now, like if I defined an array, so if I wanted to define an array, I would literally overwrite the NumPy array. So I don't want to do that. I want to do, I'd always want to do np dot array. Right, so everything's nicely contained within the NumPy module. Very, very standard. It's the same thing for pandas. You'd import pandas as PD. You can also see the imports coming in. Pandas isn't installed at the moment, but that's because I've used the virtual environment. We're not talking about pandas anyway, but if I was talking about pandas, I'd pip install pandas. Let's go back then and have a little bit more of a look, shall we? We were on there, we were on the Burke. So it's interesting that that code worked anyway. This code refines an array of sizes 2 and 3. There's the 1, 2 pieces there, and they're each of 3 elements. Composed of 4-byte little endian integer elements on my 32-bit platform. That was his 32-bit platform. My thing, when I didn't put in the D type, so here I'm not going to specify, not in the make array, but in the NumPy thing here. If I don't specify the type and run that code, F5, I get int 64s. Right. So we can index a 2-dimensional array using 2 integers. Right, so if I want to get part of the array, so we've got this array, where is it? From the book. So if I wanted to print like number 5, this is element 0 and this is element 1. So I'm going to go to element 1, so I'm going to write it here. This one's element 0, this one's element 1. So I need to go to element 1, and inside 1, this is index. I'll colour it in a different colour here. This is 0. This first index is 0, the second one is 1, and the third index is 2. So if I wanted to get this number, I'll do a quick undo of that one. So if I wanted to get this particular number, it's going to be 1, 1. The red one, because it's the second index, the second list, or the second array in the array. So it's going to be 1, and it's the second item in the array. Remember, the counting always starts from 0. Right, all counting starts from 0. I think it's VBA. It's the only language that counting that I know of doesn't start from 0. But anyway, we could print A, and then to get the item 1, is it 1, 1? Is it like that? Yeah, I think that should be it. The value of element 1, 1 is this, and then it should be the number 5. Hopefully, if it works. Boom, let's run it. I'll put is here, but yeah. Oops, how about putting it inside the string is. Boom. Just run it. The value of element 1, 1 is 5, right? So that's how we extract things from the array. And then he goes on, all code in the shaded boxes in this book have been automatically executed in a particular version of NumPy. The output of the code shown below shows the version of NumPy. So yeah, we could do input. So here is import NumPy print version. His version is 1.0.2.dev, whatever it is, and I'm going to do. Notice even the print statement's different. I can't get the double underscores there. So I could print, do that bit. It's going to forget all parts of it though. So you know what I'm going to do? I'll just do print open brackets np dot double underscore version. There we go, and run that. 2.3.2. So there's one. God knows how many versions would have gone in between, but we've got a major version, and then a second like medium thing, and then a like minor bit over there. So that's what it is. So there's probably quite a lot of versions. I'll assume one every couple of years or something like that. Data type descriptors in NumPy. An ND array is an n-dimensional array of items where each item takes a fixed number of bytes. So in here it is kind of like this is sort of like the important bit, I guess, or the crux of it all. Typically, this fixed number of bytes represents a number, an integer or floating point. However, the fixed number of bytes could also represent an arbitrary record made up of any collection of data types. NumPy achieves this flexibility through the use of the data type dtype object. Every array has an associated dtype object which describes the layout of the array. So layout of the array data. Every dtype object in turn has an associated Python type object that determines exactly what type of Python object is returned when an element of the array is accessed. So we go here, and it's almost you've got the header, so there's some sort of overhead. You've got the data type, and yeah, it's like this contiguous block of whatever the data type is, I guess, and so forth. The dtype objects are flexible enough to contain references to arrays of other data type objects. So it's an array, you can point to another array. And therefore can be used to define nested records. This advanced functionality will be described better in detail later, as it is mainly useful for the rec array, record array subclass. That will also be defined later. However, all ND arrays can enjoy the flexibility provided by the dtype objects. Figure 2.1, so I'm presuming that's this figure here. Yeah, it is this figure because it says 2.1. Provides a conceptual diagram showing the relationships between the ND array and its associated dtype object, and an array scalar that is returned when a single element of the array is accessed. Note that the dtype points to the type of object of the array scalar. The array scalar is returned using the dtype object as a particular element of the ND array. So every dtype object is built in one of the 21 is based on one of the 21 built-in dtyped objects. These built-in objects allow for numeric operations. So I'm kind of going to forward a little bit, I think. Fundamental data. Yeah, there's different types. Anyway, I think I'm just going to terminate it here because a call's coming in. But I guess I'll start streaming more. We're on page 21. We've got a long way to go. So I'll do another session afterwards because I know this is going to have lingered on. If you think you like this, put thumbs up, follow, like, and all the rest of it. And bye.